In the last tutorial, we covered A-B testing and multivariate testing. In this tutorial, we will be learning about the third type, that is multi-arm bandit testing. When you run an A-B test or a multivariate test, in your quest to maximize conversions or whatever metric you're optimizing for, there is a cost that you incur. A big portion of your traffic is routed to a losing variant, directly reducing the business metric that you are trying to maximize. Multi-arm bandit testing solves for this. But before we get into more details about multi-arm bandit testing, let me tell you a story. Yes, you heard it right, a story. They say a good story never dies. So I'm going to be using stories throughout this course to really solidify the learning. So here goes. Jim is a user experience analyst. He works with a mobile brand that is launching its latest and greatest handset next week. To hype demand and trigger wildfire sales, Jim decides to run flash sales on its mobile app for 3 days. Here is a rider though. Jim is aware that the brand's in-app navigation is poor and visitors face friction while locating the product. He ran a survey with active users to arrive at this conclusion. To improve the navigation, he decides to do an experiment. He creates a variation with a more intuitive navigation to test if this version would solve discovery issues for the new handset. So basically, Jim is trying to improve a crucial KPI, percentage of sessions in which users were able to discover the new handset. He looks at incoming data from the experiment and observes that the tweaks to the in-app navigations are demonstrating strong uplift. Jim is too trigger happy though. He wants to share early results with senior leadership and get them equally excited. He wants to convince them to direct more traffic towards the new navigation before the flash sale begins. Just as he's about to barge into the CMO's cabin, he is stopped in his tracks by a comment from a data scientist. She asks him, Jim, these trends are great, but are they statistically significant? But we don't have time to wait for it. The sale ends in 3 days, Jim grunts. So that was our little story. Hopefully the background and situation is clear. So now the question is, who is right? Jim, who is tasked with doing the best possible within 3 days, or the data scientist, who is questioning statistical significance? Well, both are, and here's why. The data scientist is right in asking the question about statistical significance because that is how we determine whether the results from the test are valid. But Jim's situation warrants an approach that minimizes the cost of running an A-B test. He needs to be able to quickly determine the winning variant and direct traffic there so he can maximize conversions during the flash sale. The loss of conversions due to low performing variations in an A-B test is called Bayesian regret. Minimizing the regret is especially important in time-sensitive situations or in cases where the cost of poor variations is high enough that businesses hesitate to run A-B tests. Since Jim is relying on a 3-day window to maximize sales, he can't wait for statistical significance and lose out on conversions, which sometimes takes weeks or months for low traffic websites. This is where multi-arm bandit testing comes into picture. If Jim had multi-arm bandit algorithms to use, this issue wouldn't have happened. We will soon see why that is. Now that we have this context, let's revisit our original question. What are multi-arm bandits? Multi-arm bandits, or I'm going to call them MAB in short, is a type of A-B testing. It uses machine learning to learn from data gathered during the test to dynamically increase the visitor allocation in favor of better performing variations. What this means is that variations that aren't good get less and less traffic allocation over time. Core to MAB is the concept of dynamic traffic allocation. It's a statistically robust method to continuously identify the degree with which a version is outperforming others and route the majority of traffic dynamically and in real time to the winning variant. What MAB guarantees is that unlike A/B test, during the course of the test, the total number of conversions will be maximized. The trade-off with A/B test is that statistical certainty takes a backseat in MAB because the focus is on maximizing conversions rather than on finding out the exact conversion rate of all variations. Let's look at how dynamic traffic allocation works in action. First, let's imagine we are doing an A/B test with 3 variations, including the control. On the x-axis here, we have time, that is which week we are in since the start of the experiment. And on the y-axis, we have the traffic allocation across the 3 variations. We can see here that the allocation at the start of experiment was 1/3 towards each variation, and it stays constant over time. Now let's look at what happens in the case of multi-arm bandit testing. Even though we start with a third split across the 3 variations, with time the allocation keeps changing with a greater allocation to the variation that is winning. In this case, the dark blue is the winning variation, and we can see the allocation keeps increasing with time. Eventually, the algorithm fully exploits the best option. In this way, the bandit algorithms mitigate regret, which is the lost conversion opportunity you experience while testing a potentially worse variation. This is explained really well in this chart by Google through an example where they simulated different scenarios to compare A/B test and multi-arm bandit. There is an interesting article where Google shares the specific example and what the intermediate results of the simulations were. I have provided the link in the course notes if you're interested in reading the complete article, but we will cover key findings here. So in this case, the experimenter was looking at 6 variations. Assume that out of the 6 variations, variation 2 is the optimal one. That is, it has the best conversion rate. We can see that the second one has the highest conversion rate. The cost of a non-optimal variation is basically the difference in its conversion rate from the conversion rate of the optimal variation. So for example, the cost of the non-optimal variation 1 is nothing but the conversion rate of 2 minus the conversion rate of 1, because 2 is our optimal variation. So that gives us 0.01 in this example. Now in the classical experiment, that is the A/B test scenario, each arm is allocated 1/6 traffic per day. If we multiply the number of observations assigned to each variant by the variance cost and then sum across the variance, we will get the cost of running the experiments for that day. So basically, visitors assigned to each variation multiplied by the cost of the variation. If you take that and you sum that across all the variations, then you get the total cost of running the experiment for that day. Let's say it works out that the classical experiment costs us 1.333 conversion each day it is run. The daily cost for both these experiments were recorded over the course of the experiment, and they were put on a graph. So let's look at the graph. You can see the flat line, which is for the A/B test, shows a constant daily cost of 1.333 as we calculated. The red line, however, shows the cost to run the bandit each day. We can see that as time moves on, the experiment becomes lesser and lesser wasteful as inferior variants are given less weight. Overall, if you take the area under the curve for each, you can see that the total cost of MAB is far lesser than what we have for the A/B test. Okay, so let's recap. In this tutorial, we started with a great story about where multi-arm bandit testing comes into play. We learned what multi-arm bandit testing is and went into detail about dynamic traffic allocation, a concept that is central to multi-arm bandit testing. That's all for this tutorial. In the next tutorial, we will compare and contrast more real-world scenarios to understand when it makes sense to use MAB and when A/B test may be a better choice. So see you in the next tutorial.